Today we're going to do B1, and practice B has to do with parallel. Now, parallel and series are different in that last time when we learned about series, we talked about the current was the same throughout. And then we said the voltages added up across each resistor, and then we just added the equivalent resistance. It's different in parallel. So we have to make sure that this is something that we're just going to have to memorize as far as the equations, looking at parallel as compared to series. Now, problem 1 relates to the sample problem, but we're going to go ahead and we're going to rework the sample problem, and then we're going to work everything that we want to do in problem 1, and I might do some extra stuff just to explain as we go along. So the first thing I'm going to do is I'm going to draw the schematic diagram. Why am I bothering to draw the schematic diagram when it's already on the piece of paper? Well, when we get to more complex circuits, we're going to be drawing intermediate schematic diagrams, and the schematic diagrams are going to help us to understand the problem. So we'll just go ahead and redraw the schematic. Now, in the diagram that's on the sheet, they don't label the resistors. When we have a bunch of resistors, it can get complicated, so what you need to do is you need to label them R1, R2, R3, R4, etc., so we don't get confused. So there's 9 volts coming out of the battery, and then our resistors, I'll just number them in order. So I'll call this one R1 is 7 ohms, R2 is equal to 5 ohms, R3 is equal to 4 ohms, and R4 is equal to 2 ohms. And I'll write my given the old-fashioned way, so again I don't get confused as far as what each of the resistances are. And what do I want to find? Well, they found the equivalent resistance in the sample problem, but we'll go ahead and calculate that. So I want to find the equivalent resistance, which I just happen to call RT. I want to find the total current, and then I want to find the current going through each resistor, which would be I1, I2, I3, and I4. And while I'm at it, I'll find V1, V2, V3, and V4. Now, I have to remember now that I'm doing parallel. So in parallel, the current divides. So the total current is equal to I1 plus I2 plus I3, and in this case I4 because I have 4 resistors. The voltage is equal. So the voltage is equal to all the equivalent the voltages across each resistor. And then to find RT, I use the equation 1 over. So this is for parallel. Okay, so for the first part, I want to find the equivalent resistor. So what does that mean in layman's terms? That means instead of having 4 resistors in parallel, what if I wanted to replace them with 1 resistor? So this would be equivalent to those 4 in parallel. That's why it's called an equivalent resistor. Okay. So how would I find that? Well, I would find that by using the equation 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3 and 1 over R4. Now, if these were whole numbers like they are, instead of just putting the numbers in my calculator, I would use fractions to do it, and I'll show you why. So that means that 1 over RT is equal to 1/7 plus 1/5 plus 1/4 and plus 1/2. Now, these are not easy numbers, but I'll try and see the common denominator between all these is actually 140. So 1 over RT is equal to 20 over 140 plus 28 over 140 plus 35 over 140 plus 70. If you feel confident that you're not going to make a mistake doing it the old-fashioned way, go ahead, but I'll show you why. So 1 over RT is equal to 143 over 140. Now this is where people make a mistake. They'll say RT is 153 over 40, or whatever that comes out to be numerically. Is that correct? No, because it says 1 over RT, so I have to cross multiply. So RT is equal to 140 over 153, which if I do on my calculator comes out to be 0.92. Now, sometimes on the test we'll have easier numbers where, like if I have 1/3 and 1/4, you know, the common denominator is 12, and it's really simple math to do in your head. But the most common mistake that people make is, instead of putting, they forget that 1 over RT when you're actually solving for RT, so then you would need the reciprocal. Okay? It happens over and over again. That is the most common mistake. So if I was to replace these 4 resistors in parallel with one equivalent resistor, that's what it would be, and it would have the same effect. So this one is equivalent to those 4 in parallel. Okay, now they want me to find the total current and then the current across each branch. We're going to always be doing the same thing over and over again. We're going to be applying Ohm's law. So Ohm's law says V is equal to IR. So I will apply Ohm's law for the total circuit. So VT is equal to IT times RT. So the total current, IT, is equal to VT over RT, which is equal to 9 volts over 0.92 ohms, which comes out to be 9.8 amps. So what that means is, here's my battery. The current is what's flowing through these wires. And this is going to help us to understand parallel circuits. How do I know something's in parallel? The current going through each of these resistors is different. And let's show you why. So here's my total current coming out of the battery. So think about water flowing through a pipe. When it gets to this point, part's going to go here and part's going to go here. So it divides. Then when it gets to this point, part goes here and part goes here. It divides again. Then it's going to be here and it's going to divide. So what's flowing, what's coming out of this battery is not the same going through each of these, and that's how I know something's in parallel, because it's split. So the way to tell by looking at the schematic diagram whether something is in series or parallel is you look at the way that the current is flowing. Is there one path for it to take, or is it dividing? When we get to complex circuits tomorrow, what we're going to have to do is we're going to have to be able to look at schematic diagrams, and we're going to have to know how we're going to simplify the circuit to intermediate schematics. What I mean is there's a certain order of operations. You know, in math, when you look at an equation and you have to know, do I do the multiplication first or do I do the addition? So you know how there's rules for order of operations in math? The same thing applies to circuits. You have to know the rules for series and parallel and know when can I start combining these. So the key is to be looking at the current going through the wires. All right, now the easy part is, now let's say I want to find V1, V2, V3, and V4. I know they're all equal because the voltage drop across here, 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 and here is the same, because in parallel the voltage is the same. So VT is equal to V1 is equal to V2 is equal to V3 is equal to V4. So I'll just write it out. V1 is equal to 9 volts. Ooh, what did I do up here? R4 was 2 ohms, and then VT was 9 volts. No one said anything. Okay, so V1 is 9 volts, V2 is 9 volts, V3 is 9 volts, and V4 is 9 volts. So now, when I want to find the current, I'm going to use Ohm's law again. V is equal to IR. So I is equal to V over R. But what I'm going to do now is I'm going to apply this for each individual branch. So I1 is V1 over R1. So it's 9 volts over 7 ohms, and it comes out to be 1.29 amps, which we'll just say 1.3. I2 is equal to V2 over R2, so it's 9 volts over 5 ohms is equal to 1.8 amps. I3 is equal to V3 over R3, which is 9 volts over 4 ohms, which is equal to 2.25, so we'll say 2.3 amps. And then I4 is equal to V4 over R4, which would be 9 volts over 2 amps, which would be 4.5. Now, we're so lucky we're doing circuits, because the great thing about circuits is you have a foolproof way to check your work every time. So in circuits right now, this is a parallel circuit. I just found all these individual currents. So if I want to check my work, I know that in parallel, the currents need to add up to the source. So I'm going to add these up, 1.3, 1.8, 2.3, and 4.5, and these should add up to be IT, so these should add up to be 9.8. Now, sometimes it might be a little bit different because you notice I rounded and stuff like that. So if these add up, then I know I didn't make a mistake. So we always, always, always have a way to check your work. So every time you do a problem, you're going to check your work. Now, when we do complex circuits tomorrow, what we're going to do is we can go through and check our work intermediately while we're using different types of schematics as we're solving it. So we check our work as we go along. So that's parallel. And that's it. Practice makes perfect.